Hello, welcome to the lecture for section 6.3, inverse trig functions. All right, before we talk about inverse trig functions, let's do a quick review of inverse functions, at least from a conceptual perspective. All right, say this is a function f, and it has an inverse. I don't know what this function does. It doesn't really matter at this point. We just want to talk about the concept. All right, so there's a function f, there's its inverse, f negative 1, or f inverse. And a function, if it takes as its input, say it takes as its input some value for x, what it's going to spit out of the function is f of x, right? Or we might call that y if it wasn't function notation. Well, the inverse of the function f will take as its input the outputs of f, and the outputs of f inverse would be the inputs of f. Y'all remember this diagram when we talked about inverse functions? Well, trig functions have the same situation. Say we have the trig function, the sine function, right? It takes as its input some angle measure, theta, say, for example. And then what it would input, what would come out of the sine function would be some ratio, call it the sine of theta, or maybe a y or something. So the inverse of the sine function then would be sine negative 1. It takes as its input the ratio that is the sine of the angle, and it gives as its output the angle. All right? So the inverse, and we can have this for the cosine, the tangent as well. So inverse trig functions do the same thing as other functions, as other inverse functions do. All right? An inverse of a function undoes the function, right? An inverse of a trig function undoes the trig function. Or in other words, an inverse trig function is what we use when we're looking for an angle measure. All right. Okay, so recall that when we have an inverse function, or if one requirement, I should say, to have an inverse function is that a function is one-to-one, right? If a function is not one-to-one, we can't find its inverse. Well, trig functions are not one-to-one, are they? If we think about the graph of the sine function, I mean, it's something like this, but it keeps on going, right? It would just keep on going. And the cosine function, does the same thing. The cosine function, recall, that's just a horizontal shift, right? Horizontal shift of the trig function. Looks something like that, right? It's not one-to-one, clearly. I mean, we can think of all sorts of horizontal lines that would intersect the function in more than one place. So it doesn't pass the horizontal line test, and it is thus not one-to-one. So in order for us to have an inverse of a trig function, we need to restrict its domain. We need to restrict its domain such that it is one-to-one. All right. The way that we restrict the domain for the sine function is from negative pi over 2 to pi over 2, right? Or we take just this portion of the graph right here that's between pi over 2 and negative pi over 2. Why do we choose that portion? Well, we try to restrict the domain so that it includes the angle 0. All right. So the sine function is restricted to just this portion, negative pi over 2 to pi over 2. If we think about that from the perspective of the unit circle, right? For the sine, what we're restricting our domain to is quadrants 1 and 2. I'm sorry, 1 and 4. Quadrants 1 and 4. Right? Because up here is pi over 2, and down here is negative pi over 2. All right, so that's for the sine. And then for the cosine, we do a similar thing. We restrict that domain as well, but for the cosine, we use 0 to pi, right? So for the cosine, we're just using this portion of the graph here from 0 to pi. Okay. From a unit circle perspective, the restricted domain for the cosine is quadrants 1 and 2. Because, of course, 0 degrees is over here and pi degrees is over, or pi radians, I'm sorry, radians is over here, right? So for cosine, we're using this just the top half of the unit circle. For the sine, we're just using the right half of the unit circle. All right, we haven't talked a lot about the tangent. We haven't focused on it too much, but we will use an inverse tangent function. So we should take a look at what the graph of the tangent curve looks like. That's this graph here in red. It's kind of interesting, right? We can see that the tangent function actually has vertical asymptotes. It's still a periodic function, right? So it's still not going to be 1-to-1. You know, it doesn't pass that horizontal line test, not at all. Why does it have these asymptotes here? Well, recall that the tangent, remember the identity? It says the tangent is the sine over the cosine. We also, the ratio, the tangent definition is the ratio of y over x coordinate of the terminal point on the unit circle. Well, we're always going to have a vertical asymptote when there's a denominator that can be 0, right? So whenever the cosine is 0, we have a vertical asymptote. Or whenever the x coordinate of the terminal point on the unit circle, right, is 0, then we have a vertical asymptote. All right, so here's we limit the domain of the tangent function from negative pi over 2 to pi over 2, just like the sine, all right, because we want to include that angle 0 in it. All right, note that for the tangent limited domain, we have to use parentheses here. On the sine, look at the sine, we had the square bracket. Well, that's because the boundaries of that interval are just fine on the sine function, pi over 2 and negative pi over 2. The boundaries of the interval are not okay on the tangent because the boundaries are actually a vertical asymptote. So we can't include that in that interval because the graph never, ever gets to that point. Approaches it, gets as close as you want, but it never actually gets there. All right, so we limit the domain to the sine function, negative pi over 2, pi over 2. The tangent function, same. And we limit the domain on the cosine function to 0 to pi. All right, so a nice summary of some information. We relate all the characteristics, I should say, of the inverse functions, right? So we're limiting the domain for the sine function to negative pi over 2 to pi over 2. And then the best way to think about this, or one way to think about this anyway, is if the sine of some angle theta equals a, then the inverse sine of a would equal theta, right? So that's just showing us that the domain and the range swap places, right? Or the input and the output swap places, right? The inputs and the outputs swap places. And that's what happens with inverse functions, right? So here we have the graph of the sine, the inverse sine function. It's just a reflection of the sine function about the line y equal x, right? The cosine, similarly, we restrict the domain 0 to pi, but if the cosine of theta is a, then the inverse cosine of a is theta, okay? Similar thing for the tangent. We restrict that domain negative pi over 2 to pi over 2, right? So again, a way to think about the inverse trig function is we use it to find an angle, right? So this would read the inverse sine of a equals theta, okay? But we could also say that this is the angle whose sine is a, right? Inverse sine of a could also be thought of as the angle whose sine is a. All right, again, yeah, inverse to swap domain and range. So that means the inverse sine function would have the domain -1 to 1 and the range -π/2 to π/2. Okay, cosine, same domain, range 0 to pi. And then inverse tangent function, the domain is all real numbers. The range is -π/2 to pi. Why is the domain all real numbers? Well, look back at the range of the tangent function. Look at the graph. The graph goes up to positive infinity and down to negative infinity. So the range has to be all real numbers. All right, let's look at some examples. Say I want to evaluate the inverse sine of 1/2. Well, for known values, it's not that bad. We can just take a look at the unit circle to find that angle. The inverse trig function is used to find an angle measure, right? So this first one says inverse sine of 1/2, or what is the angle that has a sine of 1/2, right? We'll go over here to our unit circle, and where do we see a sine of 1/2? Well, sine is the y-coordinate of the terminal point, right? So I think it's right there as a sine of 1/2. So pi/6 is the angle whose sine is 1/2. Or we could say the inverse sine of 1/2 is pi/6. Now you might be saying to yourself, well, wait a minute, isn't there another one over here? Look, there's a sine of 1/2 at 5 pi/6. But recall that when we're dealing with the inverse function, we have to restrict the domain. Okay? We'll restrict the domain of the sine to quadrants 1 and 4. Okay? So we don't want that one. It's not in the restricted domain. What about the inverse sine of -√2/2? What quadrant is that going to fall in? Well, we're restricting our domain again to 1 and 4. If the sine of the angle is negative, the y-coordinate of the terminal point is negative, well, that means we're down here in quadrant 4, right? So where is that sine of negative square root? There it is. There's -√2/2. So it looks to me like that's happening at, now we're tempted here, we'd be tempted to say 7 pi/4, but that's not in the restricted domain, is it? So we want to say -π/4, which is the same thing as 7 pi/4. But because we're finding an inverse function, we want to provide an angle measure that's in the restricted domain. So this is going to be -π/4. Right? Inverse cosine of -√3/2. Now we have a different domain we're dealing with here, right? Our restricted domain on the cosine is quadrants 1 and 2, or the top half of the unit circle, right? So where is that cosine going to be negative? That's cosine is going to be negative over here in quadrant 2, right? So where do we have a -√3/2 for the cosine? Cosine is the x-coordinate of the terminal point. So it looks like 5 pi/6 is the angle that we want for inverse cosine of -√3/2. Okay, so again, we can only look in quadrants 1 and 2 for the cosine. We don't have any negative cosines over here in quadrant 1. Tangent, let's see, where is a tangent going to be 1? Positive 1. Where's a tangent going to be positive? Tangent is restricted to 1 and 4, or the right half of the unit circle, right? So right, yeah, see no marks on here. So we're on the right half of the unit circle. Where would the tangent be 1? The tangent, recall that the tangent is the ratio y/x, whereas an identity, right, it's a sine over the cosine. So it's only going to be 1 where the sine equals the cosine, or y=x. Okay, so where is that going to occur? That's only going to occur right here at pi/4, where both the x-coordinate and the y-coordinate are √2/2. Okay, only once, only up here in quadrant 1, because down in quadrant 4, look, when we make that ratio of y/x, it's not 1, it's -1. It's -1. All right. So let's look at a few more examples. Here we have some triangles, some right triangles. Let's see if we can use our inverse trig functions to solve for the indicated angle. Okay. Now, one thing we want to keep in mind here These are all going to be acute angles. So we're really only caring about quadrant 1 for these particular applications. All right. Okay, so looking at this first triangle here, we want to solve for A. We want to solve for angle A. All right. And we know the length of the adjacent side and the length of the hypotenuse. Now we could find that length of the opposite side with the Pythagorean theorem, but we don't really need to. We can just deal with what we know. We know the adjacent and the hypotenuse, and we know that the cosine is defined as the adjacent side over the hypotenuse side, right? So we know here that the cosine of A is 6750 over 8100. All right, that we know. So we're looking for an angle. We're looking for an angle that has a cosine of 6750 over 8100. Right? So I can think about it that way. Looking at the unit circle is not going to help me here, right? That's not something I'm going to find on the unit circle. But if I want to solve for A here, all I really have to do is take the inverse cosine of both sides of this equation. It would be the inverse cosine of 6750 over 8100. Okay, if I take the inverse cosine of both sides, oops, did something wrong here. That was supposed to say just cosine there. If I take the inverse cosine of both sides of this equation, the inverse cosine undoes the cosine, right? They undo each other, right? So A then is simply going to be the inverse cosine of the 6750 over 8100. All right, what is that? Let's see what that is. Let's use the calculator. Coax my calculator, wake up. There we go. All right, so the inverse cosine is second cosine key. All right, so there's inverse cosine of, now let's see, 6750 divided by 8100. All right, so 0.5856. Now, is that a radian or is that a degree? It's pretty small. It's probably a radian, right? But look, I was supposed to find a degrees here. I might not be in the correct mode. Let's check. Let's click the mode key. Am I in radian mode? Yes, I am. I want to be in degree mode here because look, we were looking for something in degrees. All right, so let me just switch that to degree mode. All right, quit. And let's try that again. I think I'll just do second enter, which is the entry, the blue entry function. It just repeats the last thing I typed in. All right, and there we have it in degrees. 33.557 or 33.56 degrees. Okay. Look at this one here. Similar situation. Now our angle is X. We're going to assume it's degrees. We're going to stay in degree mode for a minute. In this triangle, I know the opposite side and the hypotenuse, but I don't know the adjacent. Well, since the sine is defined as the opposite side over the hypotenuse, I think I want to use inverse sine here, right? And the reason why is I can say that the sine of X is equal to opposite, that's 2.5 over hypotenuse. That's 5, right? Take the inverse sine of both sides. Let me just save some space here. All right, so we take the inverse sine of both sides. And we see that X is the inverse sine of 2.5 over 5, or the inverse sine of 1/2. Well, we could get that from the unit circle. That's on it. We're on a roll with the calculator, so let's just use the calculator here. The inverse sine is second sine, 2.5 over 5, or 1/2. We'll do it this way. And we see that it's 30 degrees, as the unit circle would tell us the same thing, right? Look, go back up here. Where's the, here we go. So where's the sine 1/2? Right here. Right there. And that, of course, is at 30 degrees. Excuse me. One more. This triangle, for angle x here, we know the opposite and the adjacent. Well, since the tangent is defined as the opposite over the adjacent, an inverse tangent function is probably is what we're going to use to get that angle, right? So I know that the tangent of angle x is equal to opposite over adjacent, right? 300 over 400, right? So if I take the inverse tangent of both sides, the inverse tangent undoes the tangent, and I see that x is equal to, let's see, inverse tangent is second tangent key, tan key, and then 300 over 400, or 3/4, or 0.75, all the same thing, right, is 36.87 degrees. Right? Let's look at a different kind of example. Here we have, oh, look at this. This is a composition of trig functions, right? If we want to evaluate the inverse cosine of the sine of pi over 6, right? Well, one way to do this is to say, well, first let me see what the sine of pi over 6 is. And that's going to be on the unit circle, isn't it? So let's go look. Pi over 6, the sine of pi over 6 is 1/2. All right, so if I know that, I could then just simplify it and say this is the inverse cosine of 1/2, right? So what angle has a cosine of 1/2, right? What angle has a cosine of 1/2? We'll look back at the unit circle. Where's the cosine 1/2? The cosine is 1/2 when the x coordinate of the terminal point is 1/2. That's right there at 60 degrees, or pi over 3. Let's switch back to radians for now. So we're going to say pi over 3. I don't see, I've got pi's here. That's telling me I want to deal with radians. Okay, so that's one way. You know, I can, if it's a known value or something from the unit circle, it's pretty easy to figure it that way. But look at this next example. Here I want to find the sine of the inverse cosine of 4/5. And 4/5 is nowhere on the unit circle. So how am I going to solve that? Well, let's do that. Let's make a triangle for that. All right. So we want to find the angle, or we're interested in the sine of the angle whose cosine is 4/5, right? Well, the cosine, recall, is the ratio of the adjacent side over the hypotenuse in a triangle. So we could draw a triangle here that has an adjacent side of 4 with a hypotenuse of 5. All right, and it needs to be positive. So I think I want to stay on to put it over here. I want to stay in quadrant 1, where the cosines are positive in the restricted domain. All right, so I'll draw my triangle like that, as if it were in quadrant 1. There's some angle here. Cosine is adjacent over hypotenuse, and it's going to be 4/5 for this guy. Right? Cosine is 4/5. It's a 5. So adjacent side would be 4. Hypotenuse over here would be 5. So we don't know what the opposite side is. Let's call it y. But we can certainly find it. We would need it too, wouldn't we? To find the sine of this angle, whatever this angle is, right? To find the sine of it, I need to know what y is, because the sine is the opposite over the hypotenuse. Well, we can find y. Let's do it with the Pythagorean theorem. 4 squared plus y squared is 5 squared, right? So 16 plus y squared is 25. Subtract the 16. Y squared is 9. So y then is the square root of 9, or 3. Can it be negative 3? No, I'm up here in quadrant 1, so I know it's positive 3. All right. So now that I know that, I could say that the sine of this angle, whose cosine is 4/5, this angle here, we're just saying the angle was theta. We don't even need to know what it is, do we? We don't need to know what that angle is, because the sine is going to be the opposite side over the hypotenuse. And for this triangle we just made, the opposite side is 3 and the hypotenuse is 5. So the sine is 3/5. Now you might be thinking, well, could I have used my calculator for that? Yes, but if you need an exact answer, right? If you see the word exact in My Open Math or anywhere, if you need an exact answer, you don't want a repeating decimal, right? Let's see, what will our calculator tell us for this? We want to find the sine of the inverse cosine, so that second cosine, the inverse cosine of 4/5. Not a repeating decimal, so we're good. I could also call that 0.6. And this one would have been fine to solve this way or with the calculator. Let's look at the next one. This one is the sine of the tangent, the inverse tangent, sorry, of 7/4. All right, what does the calculator tell us that one is? The sine of the inverse tangent, okay, of 7/4. That's a very ugly decimal. If I need an exact answer, that calculator is not going to be good. I'm going to need to do a triangle and deal with it this way. All right, well, the tangent is positive. We're restricted to quadrants 1 and 4 in the unit circle. All right, the tangents are going to be positive only in quadrant 1. All right, let's look at it again. Remember, tangent of pi over 4 was positive. Tangent of 7 pi over 4 was -1. All right, for that. Okay, so we're going to be in quadrant 1. Let's make a triangle that we can deal with in quadrant 1. Tangent, recall, is defined as the opposite side over the adjacent side in the triangle. So for this triangle, I don't know, maybe it'll look something like this. And there's our angle. Okay, the opposite side is 7, the adjacent side is 4. Right, now if we want to find the sine on this triangle, just like we did up here, sine is opposite over hypotenuse. So I need to find what the opposite of, let's write it, opposite over hypotenuse. I need to find this hypotenuse if I want to find the sine of the angle without having to know what that angle is. Well, Pythagorean theorem again, we'll say 4 squared plus 7 squared is h squared. Let's see, that's 16 plus 49. That's 65. Take the square root. The hypotenuse is going to be the square root of 65. Okay, and I don't care about negative here, right, because I'm in quadrant 1. So that tells me that the sine, which is opposite over hypotenuse, is going to be 7 over the square root of 65. If I want an exact answer, I need this, not that ugly decimal. That's approximately equal to 0.8682. But look, squiggly equal sign, that's approximately, it's not exact. All right, let's look at one more example here. Say we have a composite trig function and we need to simplify it. Look at this one here. I can't solve this, right, because I got a variable there. I don't know what it's equal to. So I just want to find a simplified expression for the sine of the inverse tangent of 4x. Right? 4, and it's giving me a little restriction on x. -1/4 is less than or equal to x is less than or equal to 1/4. Or if I was more interested in 4x, multiply everything by 4, right? -1 is less than or equal to 4x is less than or equal to 1. It's just making sure that we stay within the domain of the inverse tangent function. That's all this requirement is saying here. All right, well, how do we go about doing this? Similar way, we just aren't going to be able to actually find numbers, right? We can still use a triangle. We're still in quadrant 1 here because, well, no, it doesn't matter. We could be in quadrant 1 or quadrant 4. We know we're restricted to 1 and 4 with a tangent, all right? But since x could be positive or negative, it doesn't really matter. I don't even really need to think about it, right? So let's see. If we can do this with a triangle like we did the last one, we'll say that's our angle. Oop, it's supposed to be, oh, I'm just going to let it be that. All right, so the tangent, of course, is the opposite over the adjacent side. But I don't have a ratio here, do I? It's just 4x. Well, I could certainly call 4x over 1, couldn't I? So then I could say the tangent is 4x over 1, and I could say my opposite side is 4x, and my adjacent side is 1. All right, now if I want to find the sine of this angle, I'm going to need opposite over hypotenuse. So I'll need to solve for that hypotenuse with the Pythagorean theorem, right? So the hypotenuse squared is equal to leg squared, that'd be 4x is one of the legs, plus 1 squared, right? Let's simplify a little bit. 4x squared, of course, is 16x squared. When we square the whole 4x, 1 squared is just 1. All right, now take the square root. H is going to be the square root of 16x squared plus 1. All right, now that I have an expression for that hypotenuse, square root of 16x squared plus 1, it's not too hard to write the sine. Sine, again, it's the opposite over the hypotenuse, right? And the opposite over the hypotenuse here is going to be 4x over the square root of 16x squared plus 1. All right. That ends the lecture for section 6.3, inverse trig functions.